Welcome back, class. We're going to continue in Whitlock and Schluter Chapter 11, moving into confidence intervals. Okay, so we're going to do this example from Whitlock and Schluter, page 263. And we're talking about this fly, which has these eye stalks. And we want to get the 95% confidence interval for the mean span of stock-eyed flies. Sample size 9, sample mean standard deviation are given. Okay, we're going to use the typical 4-step procedure for doing confidence intervals that I've already laid out before. As we get into it, let's check our assumptions. Okay, do we have X normally distributed? Well, it doesn't say, so we're going to go ahead and assume that, making the assumption explicit at the beginning allows us to be clear about the limitations of our work. And we have sample size 9, so degrees of freedom is n minus 1. 9 minus 1 equals 8. Okay, so the statistic is X bar equals 8.778, and the standard error is, we use S over square root n, which gives 3.98 over square root of 9. So that's going to get us about 0.12 or so, 0.13. Now I'm going to go ahead and sketch the curve. All of these normal confidence intervals look similar, so we're going to stick the sample mean in the middle, 8.8, let's say. Now we need the margin of error. Back from chapter 4, we had a margin of error given to us, and that margin of error looked like we actually used 2 times the standard error. Now later on, we moved up to 1.96 for a 95% confidence interval times standard error. Now that we're using the t-distribution, we're going to find out where that number comes from and if we should use it here. So specifically, we're going to use a t-distribution with 5%. I'm going to put a little 2 in here denoting 2 tails, as we'll see in a moment, times standard error. And here we go. Okay, using the table, not the normal table now, but page 674, students' t-distribution table. For a 95% curve, we want to have 2.5% on the left, 2.5% on the right. So we read degrees of freedom in the row. I have 8, and alpha 2 means the 2-tailed probabilities. So this 5% column is spread on 2 tails. If you only did 1 tail, then you can see that that would be 2.5% on 1 tail. So that's how the columns work. 2.31 is the number that I need for my 8 degree of freedom t-distribution. So I put my 2.31 here, and my standard error was 0.133, product of which is, I don't have it written down there. There it is, 0.307. And so I add and subtract that to my mean to obtain 8.47 on the small side to 9.09 on the large side, and that's got it here, so I should expand that here. Okay, so on the level of the sample means, we're 8.47 to 9.09. On the level of the t-scores, we're minus 2.31 to positive 2.31. Thus, 95% confident, the true mean is from about 8.5 to 9 millimeters. Notice that we have actually discovered something about the true sample mean based upon a single sample, which is rather remarkable. Now, you might be asking, how did we do that given this central limit theorem? Didn't you say the true mean was in the center? We put the sample mean in the center. That is correct. Now let me explain. In passing, I want to note that the following R command produces the R output. So I'm just putting in the data itself. It was a single column, so this worked. Otherwise, you'll have to call that particular column, maybe do an attach or something. Confidence level, fixed it at 95%. Notice the 95% confidence interval comes out right here. That's exactly what we obtained by hand. Okay, back to this question of the confidence interval. Why did we have that 8.78 in the center? I thought you said that we had the true mean in the center. Well, there's a cute little switcheroo that we pull when we compute confidence intervals, and so I want to show it to you here. What we do is we start off with what we know, and that is the true mean is in the center. And then we take a sample, and we know the true mean here is in the center, and we're going to come up with whatever margin of error we have, just call it E. And so I have a 95% confidence interval here. Okay, 95, 2, 2, 2, 2. Okay, so when I take a sample mean, let's go in red here, sample mean, we don't know what the true parameter is. We just know that it's in the middle somewhere. My sample mean is, in fact, going to come out here, here, here. It's going to get distributed all around, but 95% of the time, it's going to be in this interval, which is around the true mean. I have that depicted here. Mu minus E to mu plus E. 95% of the time, if I let alpha in this formula be 0.95, excuse me, 0.05, then this is going to be 95%. So let's just put that on for our eyeball's sake. Okay, great. Well now, algebraically, I'm going to subtract mu from every single part of this inequality, and I get this. Next, I'm going to subtract x bar from every single part of the inequality, and I get the x bar out of the middle, the minus mu stays, and I get x bar on the ends. Awesome. I'm basically there. I have x bars on the ends and I have mu in the middle. All I'm going to do now is fiddle around. I don't need a negative mu, so let's multiply left and right by a negative, and that gives us this result. I just want to note, it's true that negative 7 is less than negative 5, right? But if I multiply both by a negative 1, what happened? Well, their sign changes because they've moved from the left to the right-hand side of the origin. So we need to flip our signs, which we did here. And lastly, I like to read a less than sign, not a greater than, so I'm going to flip the whole thing around, and that moves me into this statement. But this statement is exactly the one that I've been using all along, namely x bar is in the middle, and I'm going x bar plus e, x bar minus e, and now we don't know the mean, but there's still a 95% chance that it's going to be inside of this interval, which is a random interval, which is exactly what we want. And so for a formal probability statement, you can state it here. Great. Now, as a side note, I would like to say that these are random intervals. So if I were to obtain, let's suppose that this is the true mean. Let's just suppose it's 8.9. Then out of 100 intervals, 95 of them would contain the true mean and 5 would miss. We can see that this interval right here missed. It did not contain the true mean. And on average, 5 out of 100 will miss, but 95 out of 100 will hit it. Okay, let's consider the final example here. This is the coal car example again that we covered in Chapter 10. And so we have a sample of 40 cars with a mean of 74.5 tons per car and a sample standard deviation 0.8. Okay, now when it comes to checking assumptions, we're going to assume that these are random coal loads. You could argue against that, but we're just going to assume that. Now, what we don't have is knowledge that the variable, the parent, a single load of coal, is normally distributed. But we do have a large sample. And given that large sample, the central limit theorem is going to kick in. And so these means are going to follow the t distribution, at least approximately close enough, because of that large sample size. Okay, you can ask in class. It'd be a great question to ask. All right, so we have this basic information here of our mean and our standard error calculated. 0.8 over rad 40 is 0.13. So I'm going to sketch myself a curve. On my curve, I have the sample mean in the center there. So we're doing x bar, and then we have a t level. We need the margin of error. Okay, margin of error. Notice this is a 90% confidence interval here. And so for the 90% confidence interval, we're going to look up, and I need a 10% with two tail. So let's go ahead and pull that number from the table. Degrees of freedom is 39 because I have a sample of size 40, and the 10% two-tailed is 1.68. So I'm going to go ahead and pop that in here. On my notes I did a different one. So putting in my 1.68, multiplying, my margin of error is going to be 1.68 times the 0.13, which gives me a 0.21. So that takes me to 74.71 to 74.29. Okay, and that is my confidence interval. So we can say we're 90% confident that the true average is 74.29 to 74.71 tons. Now, the manufacturer is claiming 75 tons. So we have a problem here. We have been shorted some coal, evidently, and that's something that we would need to take up with the manufacturer based upon our data.